Hi everyone. So let's see the MOSFET circuit symbol now. So what do you mean by circuit symbol? Like we have studied diode. So diode was in physics we studied like this. This was our diode. But in the circuit analysis we were using it like this. Similarly, we have studied MOSFET like this. This is our MOSFET, but in the circuit analysis we will use it differently. So how we will use it? Like this. So first let's see about depletion type of MOSFET. So this is our depletion type of MOSFET. So these are for NMOS. These all are for NMOS. Depletion, enhancement, and common for both, like for depletion as well and for enhancement as well. And these are for PMOS, P channel. These are for P channel. These are for PMOS. So how do you denote it for depletion type? There are two solid lines. These are the solid lines. This is the solid line, and then this kind of structure. Now this potential will be drain, this potential will be source, and this potential will be body. Now there will be a sign of arrow. So how that arrow will look like? So when we study N channel, this is the P substrate and then there is N plus, right? This is our N channel MOSFET, right? P substrate and N plus. So how does the diode look like? Diode looks like this. So the arrow of diode is from, this is our body and this is our other terminal, you can say source or anything. So from body to, this is the arrow, no? Diode, arrow of diode, it is getting outward from body. So this will be the direction. And in case of PMOS, this will be the direction. This will be body, this will be source, and this will be drain. Drain. Here it is shown that source and body are shorted. Here it is shown that source and body are shorted. Because in both PMOS and NMOS, we are keeping source and body shorted. So here it is shown source and body are shorted. You can actually make it like this as well. Like it is not shorted. In that manner also you can make, but generally we make source and body are shorted. So generally you will find it like that. So drain, source, gate, body, like that. What will be the arrow direction? How do we define the arrow? The arrow is, you will, in the mind you will think, okay, my body is, my substrate is, this is my body, my substrate was P type, substrate was P type and channel was N type, channel was N type. So from P to N, this will be the diode. So arrow will be from body to inside, getting out of body. So that will be the direction of arrow. So this is how you make the arrow. And in case of PMOS, it will be opposite, because here the substrate was N. If the substrate was N, this would be the direction of arrow. So the arrow is getting into the body, the arrow is getting into the body. Well and good. Again, here similar structure is there. This will be drain, this will be source, this will be body. What will be the arrow? Same direction, inside. Here outside, this will be source, this will be drain, and this will be body. But the lines are dashed. Here dashed line is used, this is dashed, and here solid line is used. What is the reason? Solid line shows that the channel is already present, and dashed line shows that the channel is not there, you have to make the channel. Solid line shows that the channel is already present. So in depletion type of MOSFET, channel was already present. In enhancement type, we made the channel by applying gate potential. So that's why dashed line is used in enhancement type and solid line is used in depletion type. Got the point? Now, by this arrow, you will recognize whether it is NMOS or PMOS. If arrow is inward, that means it is NMOS. But arrow from body terminal, here the arrow will change. That we will talk about. So arrow from body terminal, if the arrow from body terminal is inward, that means it is what? NMOS. If the arrow is outward, it is PMOS. Now, how will you define the source and drain? It's not that the upper one will be source and lower one will be drain, and here upper one will be drain, lower one will be source. Nah. Generally it is shown like this. But this is not the case always. So the one which is at higher potential will be drain and one which is at lower potential will be source in case of NMOS. I told you, remember the last lecture. In NMOS, which one is at higher potential? In NMOS, you apply positive bias at drain. So in NMOS, which one is at higher potential? drain is at higher potential. So one which is at higher potential, in case of NMOS, that will be drain, and lower potential will be source. So if any particular circuitry is given, any particular MOS is given, they haven't shown drain and source, you don't know that, but you know the absolute potential of two nodes. You know the potential of this node is 6 volt, you know the potential of this node is 4 volt. So first you will see the arrow is inward from body, arrow is inward, that means it is NMOS. And if it is NMOS, that means higher potential will be drain and lower potential will be source. So wherever you see high potential, that will be drain, and wherever you see lower potential, that will be source. Well and good. And in case of PMOS, what will happen? The source is at higher potential, because in case of PMOS, what do? We apply negative potential at drain. Negative potential at gate. So source is at higher potential. So here I will write higher potential. I will just write HP, higher potential. And here I am writing lower potential. This is higher potential and this is lower potential. So I am also writing the shortcut higher potential. And what do you mean by LP? Lower potential. And generally it is shown like in case of NMOS, we show drain upward and source downward. Why drain upward? Because drain is at higher potential. Always higher potential is shown upward and lower potential is shown downward. Like let's assume you make this kind of structure, no? Sometimes this is ground, this is resistance R, this is 5 volt battery. So higher potential is always upward, lower potential is always downward. You won't see circuits like this. Like you can make it like this, but generally it is shown like this: 5 volt resistance and then ground. So 5 volt device and ground. So higher potential is upward, lower potential is downward. Here what is higher potential? Higher potential is source and lower potential is drain. So higher potential upward. So generally it is shown like this, but by the direction of arrow you will get to know. If from the body arrow is outward, that means that is NMOS. If the from body the arrow is inward in the body, that means that will be PMOS. Now here, if the arrow is outward, that will be what? NMOS. And if the arrow is inward, that will be PMOS. And the one which is at higher potential, that will be drain, and one which is at lower potential, that will be source. Yeah, this will be source, this will be drain. Although this shows the direction of arrow, although this shows the direction of current, this arrow shows the direction of current. In case of NMOS, what is the direction of current? Remember it. In case of NMOS, what is the direction of current? Electrons travel from source to drain. That means direction of current is from drain to source. So this is the direction of current in case of NMOS. So this is the most general circuit. In 99.95% cases, this will be used. You will see this kind of circuit in 99.95% cases. And here, this is the higher potential. This will be the lower potential. If you know the absolute potential of drain and source, then you can make drain and source by your own. If you don't know the absolute potential, let's assume there is some circuitry given like this. And some resistance R is there, some 5 volt is there. This is some resistance R, this is some V. Do you know the potential of drain here? No. Do you know the potential of this node? I'm not saying this is drain. Do you know the potential of this node here? No, you don't know. And this node is grounded. Let's assume this is also resistance R. Do you know the potential of this node? No. So by default, you will consider this as drain and this as source. And you will consider the direction of current like this, from drain to source. But if you know the absolute potential, like let's assume this structure is given. Whatever it is, it can be anything. Let's assume this is 6 volt and this is 4 volt. So you know the absolute potential now, that this is 6 volt. That means first what you will see the arrow. Arrow is outward. That means it is certainly NMOS. It is NMOS. So it is NMOS. Now the one which is at higher potential, that will be drain, and this will be source. Well and good. And here the one which is at higher potential, that will be source, and one which is at lower potential, that will be drain. And what is the direction of current in case of PMOS? Holes travel from source to drain. So the direction of current will also be from source to drain. So this is the direction of current. And this is higher potential. This is lower potential. Actually, most of the time when we study, people say that, okay, this is NMOS, just remember it, and this is PMOS, just remember it. But this is not the case. The one, this is NMOS, this is PMOS, that's for sure. But you can't say that always this will be drain and always this will be source. No. The structure of MOS is symmetrical. Drain and source can be interchanged based on their potentials. Understood this point? Based on their potential, the source and drain can be interchanged. And this is general kind of structure. This will be, again, this will be based on, let's assume this is higher potential and this is lower potential. This is how I am making. So this is our NMOS. Here there is no arrow, nothing. No arrow, nothing. Just the difference is there is this bubble there. This bubble is there. This small bubble is there. In case of PMOS, this small bubble is there. So this will be source, this will be drain. This is at higher potential, this is at lower potential. Well and good. Understood this concept? So these are the symbols. These are the most important one. These are the most important one. These are used in digital circuitry. In analog, this symbol will be used. Somewhere you can see this symbol as well, but most generally this symbol will be used. So like that, arrow is outward, that means that is NMOS. Arrow is inward, that means that is PMOS. But also the higher potential will be source and lower potential will be drain in case of PMOS, and higher potential will be drain and lower potential will be source in case of NMOS. Let's see a question and that will clear your concept now. You have to mark source, drain and the current direction. This is what you need to mark. Which one is source, which one is drain, and what will be the direction of current. So what you will do, this particular structure is given. You see, this is the arrow. That means this is NMOS. First thing I got to know is that this is NMOS. Now I know one thing. What is that? That in case of NMOS, the one which is at higher potential, that is drain. So this will be drain and this will be source. And what will be the direction in case of NMOS? What is the direction of current in case of NMOS? The direction of current in case of NMOS is drain to source. So this will be the direction of current. That is ID. If you see this structure, you will see that arrow is inward. That means this is PMOS. This is PMOS. Now in PMOS, I know one thing. What is that? The one which is at higher potential, that is source. The one which is at higher potential, that is source. That means this will be source and this will be drain. What is the other thing do I know? The other thing I know is that in case of PMOS, the current always flows from source to drain. Current always flows from source to drain. So this will be the direction of ID. Let's see this. I see this structure. What do I get to know? That this is an NMOS. Just as I see this structure, I get to know that this is an NMOS because the arrow is outward. One thing I know that in case of NMOS, the one which is at higher potential, that will be drain. So now this will be the drain. And this will be source. And what is the direction of current from drain to source? So this will be the direction of current. Now a lot of people will say, like I'm saying 99% of GATE aspirants who haven't studied analog electronics deeply, if this question is given in front of them and I say that my gate potential is 5 volt, and if I ask them what is the operating condition of a MOSFET, whether it is on or off, so what they will say? They will say that, sir, 5 minus 6, your VGS is minus 1 volt. That means VGS is less than 0, so diode is off. This is what they will say. But this is not VGS, this is drain. Because mostly what is taught is that wherever you see this arrow, that means this is source. This is wrong. Arrow doesn't mean this is source. If the arrow is outward, that means this is NMOS. That's it. Nothing else. If arrow is outward, that means it is NMOS, nothing else. Understood the point? But when you study amplifiers, you just get habitual that this will be source only, this will be drain only, because amplifiers are biased in a way that always higher potential will be upward only and lower potential will be downward only. They are biased in that way. Like with the supply, we make sure that the upper potential is drain and lower potential is source by the supply only. So in case of amplifier, you can say that, okay, sir, this will be drain, this will be source. But here I am talking about DC biasing. DC biasing. I have fixed my potential. The upper one is 4 volt, the lower one is 6 volt. That means the one which is having higher potential. Now the arrow doesn't define the direction of current. What arrow is saying? Arrow is saying that direction should be like this. This is what arrow is saying. But actually the direction is from drain to source, from down to up. Are you getting this point? And 6 volt, one which is higher potential, that is drain, and one which is lower potential, that is source. Now I see this arrow, the arrow is inward. So first thing that I got to know is that this is PMOS. This is the first thing I got to know. This is PMOS. Now if this is PMOS, what do I know? That one which is at higher potential, that is source. In case of PMOS, one which is at higher potential, that is source. So which one is higher potential? This is the higher potential. So that is source. And one which is at lower potential, that will be drain. So this will be drain. What will be the direction of current? This will be the direction of current from source to drain. Are you understanding this point? So this was a very important concept which usually aspirants ignore, but now you understood it. Okay. But in case of amplifier, you will not have to think that much that, okay, sir, which will be drain, which will be source, because they will be biased in a way that this will be drain only, this will be source only. And in case of PMOS, this will be source only and this will be drain only in the amplifiers. But here I am talking about DC biasing. In DC biasing, I can interchange anytime. Let's move on to the next concept. Before moving on to the next concept, we will solve a simple problem. So it is given that mu p, that means mobility of holes, is 0.4 times of mobility of electrons. I don't need to write it in statement, right? You will understand. The mobility of holes is 0.4 times of mobility of electrons. What must be relative width of n channel and p channel devices of relative width of n channel and p channel devices, that means NMOS and PMOS, if they are to have, that means if they are having equal drain currents when operated in saturation mode with on drive voltage of the same magnitude. What is on drive voltage? Overdrive voltage, sorry, not on drive, sorry, overdrive. What is overdrive voltage? Overdrive voltage. Overdrive voltage means VOV, we should show it, and that is VGS minus VT only. Basically, I told you that VGS is greater than VGS minus VT. If VDS is greater than VGS minus VT, it will be in saturation region. So this potential is known as V overdrive. V overdrive is VGS minus VT only. Okay. So this term I forgot to introduce you. So V overdrive is VGS minus VT. Always remember it. Arey wah. V overdrive is VGS minus VT. This is V overdrive. Both are operating in saturation mode. Both are operating in saturation mode. And they are having equal drain currents. The current is equal. So the current of PMOS is equals to current of NMOS. So what is the formula? For PMOS it will be mu P COX W by 2L. Both are in saturation mode. So that's why I am applying P by 2L. Yeah, this V overdrive is VGS minus VT. Also it can be. This is for NMOS. And what it will be for PMOS? For PMOS, if we know one thing, for NMOS, if we know one thing, what we can do? We just need to interchange. VGS will be interchanged by VSG. And VT will be replaced by mode of VTP. So this is for PMOS. Here I can write VTN. This is for PMOS. Now mu n CoX W by 2L, VGS minus VT. VT, okay, sorry. This is, we are writing for PMOS. So we will write VSG minus VTP whole square. And what we will write for NMOS? Mu n CoX W by L. Relative width if they are having equal drain current when operated in such a manner with the same magnitude of this, and even this CoX is equal. This is what should be written, that this oxide capacitance is also equal. Oxide capacitance you will consider equal because there is no information given about it, so we are considering it equal only. So here what will be the relation? Mu n CoX W by 2L VGS minus VTN square. Now what is this? VOV. And what is this? VOV only. Both are equal. But here W by L is not equal. Because they are asking, what they are asking? The relation between the width of n channel and p channel. So this W by L is not equal. So I should write W by L for PMOS. So mu n COX W by L for PMOS divided by 2. This will be the formula. Mu n COX W by L by 2 VSG minus VTB whole square. And here what will be the formula? Here the formula will be mu n COX W by L n by 2. Right? This COX and COX can be cancelled. This 2 and 2 can be cancelled. And overdrive voltage are same with overdrive voltage of same magnitude. That means this complete term is same. So what you are left with? You are left with mu P W by L P is equals to mu N W by L N. So we have to find that mu P is equals to 0.4 mu N. Mu P is equals to 0.4 mu N. Right? 0.4 mu N. So basically this mu N and mu N will get cancelled. So this I can replace with 0.4. What did I do? In case of mu P, I put 0.4 mu N. So mu N to mu N got cancelled and only 0.4 is left here. So what will be the relation between W by L of P should be 1 by 0.4. 1 by 0.4 is 2.5. Should be 2.5 of W by L of N. So if the mobility of holes are 0.4 times of mobility of electrons, then to have the same current, the width of PMOS should be 2.5 times of width of NMOS. Did you understand this point? Mobility is lower. For PMOS, mobility is lower. So to have the same current, you have to increase the width. Understood? Mobility is lower. So to have the same current, width should be increased. Right? So width should be 2.5 times of N. Very easy question. Let's move on to the next one. For a N-channel MOSFET, if the conduction parameter, look, this Kn is written there. Now, what is Kn, this conduction parameter? So sometimes Kn can be mu n COX W by L. And sometimes this Kn can be mu n COX W by 2L. In the examination, certainly it will be written. In bracket, it will be written that Kn is mu n COX W by L or 2L. Whatever they mean. If they mean W by L, they will write it. If they mean W by 2L, they will also write it. Okay. So in the examination, it will be written. So here also it is written. This is given. This is given. Given in the question. It will be given in the question. That Kn means mu n COX W by L or mu n COX W by 2L. तो कौन सा भी हो सकता है? वो डिपेंड करेगा एग्जामिनेशन में. एग्जामिनर क्या चाहता है? So it would be given. Sometimes they take mu n COX W by 2L. Sometimes they take mu n COX W by L. So it will be given. For this question, Kn is mu n COX W by 2L. Right? Now what is given? So value of mu n COX W by 2L is given. That is 0.249 milliampere volt square. The value of VGS is given, that is 2 VT. The value of VT is given as 0.75 volt. So basically this will be 1.5 volt. The value of VDS is given as 0.4 volt. You have to find the drain current. So what will be your first step? You have to find the drain current. What will be the first step? The first step will be to determine the region of operation, whether it is in saturation or it is in linear. So how will you determine it? Whether it is in saturation or linear? You will determine with the value of VDS, VGS and VT. So what is V overdrive? V overdrive is VGS minus VT. And that is equals to 0.75 volt here. What is the value of VDS? VDS is 0.4 volt. Right? VDS is 0.4 volt. So here what do you see? That your VDS is lesser than V overdrive, or you can say your VDS is lesser than VGS minus VT. That means it is in linear region. So your MOS is working in linear region. Did you understand this? What did you do? We have VGS value, VT value and VDS value. So we determined the V overdrive voltage. V overdrive voltage was VGS minus VT, that is 0.75. Then we saw VDS value. VDS value is 0.4 only. If VDS is 0.4, so it shows that VDS is lesser than VGS minus VT. So VDS is lesser than VGS minus VT. VDS is lesser than VGS minus VT. That means it is working in what? It is working in linear region. MOS is working in linear region. What is the current in linear region? The current in linear region would be mu n cox w by L VGS minus VT into VDS minus VDS square by 2. So what is the value of mu n cox w by L? Value of mu n cox w by L will be 2 times of 0.249. 2 into 0.249. What is the value of VGS minus VT? VGS minus VT is 0.75. What is the value of VDS? That is 0.4, right? It is 0.4 minus 0.4 square by 2. You just need to solve it and you will get the value of IT. Okay, let me solve it and I will write down the final answer. Yeah, so you are getting 0.109. So tell me, it will be ampere or milliampere? Milliampere. Why so? Because this is milliampere by volt square and this complete unit is volt square only. This complete unit will be volt square only because this is voltage square, this is also voltage square. So this complete unit will be volt square. So volt square to volt square got cancelled, milliampere is left. The current will be milliampere. ID is 0.109 milliampere. Well and good. Okay. Let's move on to the next concept. It's not concept, there will be a small questions. Then there will be two concepts, channel length modulation and body effect, that we will see. So first question is, how many charge carriers are there in a MOS? What is the answer? How many charge carriers are there? Only one. Only one. What is that? In case of PMOS, what is the charge carrier? Holes. And in case of NMOS, what is the charge carrier? Electrons. When we studied PN junction, how many charge carriers were there? Two. Because of holes as well, the current was generated. Because of electrons as well, the current was generated. Because of both. But here, in case of NMOS, the current is generated because of electrons only. There is no role of holes in the generation of current in case of NMOS. The current is generated because of electrons only, because N plus and N channel. So because of electrons only. So the current is generated because of electrons only. And in case of PMOS, current is generated because of holes only. But when we studied PN junction diode, the current was generated because of both. Holes were going here and these were going here. So the current was generated because of both. But here the current is generated because of electrons and holes only. So here there is only one charge carrier. And in case of PN junction diode, there are two charge carriers, both electrons and holes. What is the need of oxide layer in MOS? So when we studied MOSFET circuit, what did we study? Metal, oxide, semiconductor. So this was our MOS, metal, then oxide, and then there was this semiconductor or channel, you can say. Here we will be framing the channel. So why there is this oxide layer? What is the use of that? Okay, here there was gate potential, right? Let's assume this I am talking about NMOS. Let's assume I am talking about NMOS. Let's assume I am giving positive potential here. If I give positive potential here, what happens? Here negative potential is induced. First negative is induced, then inversion layer is formed. Why negative induced? Because here there is positive potential, so electrons will be coming inside, and there are this negative charge and a hole. So this will recombine with the hole. So only negative charge will be left. So this negative charge will be there. So when we apply a small positive potential, what happens? A small negative potential are there across the semiconductor. Now what if this oxide layer was not there? If this oxide layer was not there, what would have happened? These negative charge would have reached to this plate, this metal plate, and would have neutralized it. If the negative charge were reaching this metal plate, then there is no chance that there will be a inversion layer here. Because what would have happened? That battery is supplying electrons, and then all the electrons would have reached to this metal plate. They wouldn't accumulate near the semiconductor. They wouldn't accumulate in the channel. They would have reached to metal. Are you understanding this point? But since there is oxide layer, there will be no electron that will be reaching the metal. So there will be no current. So this gate current will be 0. And since there will be no current, that means in the vertical direction there will be no current. In this direction there is current. Because of this positive supply here, in this direction there is current, but in the vertical direction there will be no current. So because of this oxide layer, these negative potential or electron are not reaching the metal plate. And if they are not reaching the metal plate, we can make the inversion layer. And if the inversion layer is framed, then we can have the current in the NMOS. The drain current would be there. If this oxide layer was not there, then these electrons would have reached to the metal plate, and then gate current only would have been there. There would be no drain current. But we want the drain current. We want the output current. It's not that I am applying a battery and from there I am getting a current. No. So in case of NMOS and in case of PMOS as well, the gate current is always 0. Why so? Because of this oxide layer. If this oxide layer is there, that is preventing these electrons and the negative charge to reach to the metal plate. And that will frame our inversion layer and we get the drain current. So that's why oxide layer is important. So this I will write in the theory. So I will pause the video and write it down because it will just waste your time. Yeah, so this is what I wrote. Because of this oxide layer only, the electron and the negative charge near the semiconductor is not reaching the metal plate and we are able to frame the channel. And this channel helps in generating the drain current. Understood? Now the third question, why do we use MOSFET in enhancement mode of operation for amplification? That I have already explained you. Because what did we need as an amplifier? That I apply a certain input voltage and then I get a output that is depending on the input voltage. So in depletion type of MOSFET, the channel was already present. Even if you don't apply any input, you get some output, you get some drain current, and that is not desirable. Like even if I am not applying any input, still I am getting some output, that is not desirable. So here in enhancement type of MOSFET, the MOSFET doesn't conduct for zero input voltage. For conduction, your VGS should be greater than VT, and the drain current depends on the applied input voltage only. So applied on VGS voltage only, my drain current depends. So here I will apply some VGS voltage. Let's assume this is VG, this is VS, or I should write this is gate potential and this is drain potential. This is gate potential, this is source potential, then this is drain potential and this is source potential. So from drain to source there is a current, and if I am applying some VGS voltage here, from drain to source I will get some current and that will go to my output. Well and good. There will be a R0 resistance as well, which I haven't shown. From where this R0 resistance will come, that we will check. I am saying that there will be one R0 resistance as well. Now from where that will come, let's check that. So now our next concept will be channel length modulation. So ideally what we have studied? We have studied this graph of, okay, I will not show this. So ideally we have studied this, that for increasing VDS, the current will increase linearly and then it saturates. This is what we have studied. So what we have studied, for VDS greater than VD sat, the current saturates. Current saturates. But practically what happens, when you increase VDS, it increases linearly, then it nearly saturates. That means it will rise a bit. It is not saturated. Saturated would have been like this, but it will rise slightly. So even after the saturation voltage, the current doesn't saturate. It rises slightly, very low. So this I will write. Practically, for VDS greater than VD sat, current rises slightly. So this was our channel. So initially, when you, what should I color? Yeah. So initially, let's assume this is our channel. This is our channel. When you keep increasing VDS voltage, what happens? The channel start getting trapezoidal like this, and at one point the channel becomes something like this. So the time when the channel becomes something like this is our saturation voltage only. This is our VD set. So the drain to source potential or the drain potential when the channel is depleted of charge carriers from drain side. The VDS potential when the channel is depleted of charge carriers from drain side. From drain side, it is completely depleted. So that potential only is known as VD set. And then what did we say? That I further increase VDS. If I further increase VDS, what will happen? My channel will be something like this. So now my reverse bias is getting increased, but the number of charge carriers are getting less. The number of charge carriers are getting less, but my reverse bias is getting increased. So reverse bias is strong, but charge carriers are less. So eventually I will have a saturated current. So there is one phenomena. One phenomena is saying that the electric field is strong, so the current should increase. But the other phenomena is saying that there are less charge carriers, so the current should decrease. One is saying more electric field, current should increase. One is saying there are less charge carriers, the current should decrease. So what happens? The current saturates. But in practical scenes, what happens? The electric field is more dominating. In practical sense, the electric field is more dominating. They are saying that the electric field is strong, so it will increase the current, but very slightly, not linearly, very slightly. Like if this was the linear waveform increasing, and if this was the linear waveform, then this would be the practical waveform. If this was, sorry, this was the ideal waveform, then this would be the practical waveform. So what is the reason? The reason is the same. Why it is happening? The reason is the same, that when you keep on increasing VDS, what happens is that the electric field is very strong. So because of that very strong electric field, the current slightly increases. Previously, I was saying that the electric field is strong, but the number of charge carriers are less, so the current saturates. But when I see the practical scenario, I observe that even if after the saturation voltage, even if I am increasing the VDS, still my current is increasing, but very slowly. This is what I observe when I do the practical things. So this I can write, and this here I will show as well, that this depletion width is getting increased. When VDS is greater than VD sat, depletion width is getting increased. If it is getting increased, then there will be strong electric field, and this strong electric field will increase the current slightly. Increases the current slightly. Okay. So this was the practical scene, and this was the ideal, this is the practical. Actually, I have shown this slope to be high. This slope is high. This is just to show you, but in actual, the slope will be very low. It will be like this only. But this is just to show you the difference between ideal and practical graph. I am showing the slope to be very high, but actually it will be very low. And if you increase the graph, if you increase this graph in negative direction, what will happen? At some potential, if you increase the graph like this, at some potential, the current will be zero. This potential is known as early voltage. We will derive the formula. We will see what do I mean by alternating voltage. But before that, let's write down the condition for ideal case. What is the current for ideal case in saturation mode? Linear mode we are not talking about. Now we are talking about only saturation mode. So what is the current in saturation mode for ideal case? The current is mu n cox w by 2l VGS minus VT square. That is a constant for fixed VGS. Constant for fixed VGS. Here also VGS are fixed. For both of the cases, VGS is fixed. Constant for fixed VGS independent of VDS. Independent of VDS. That means even if you increase VDS, my current will be constant. This is the ideal case. Now there is a term called drain source on resistance. There is a term called drain source on resistance. So from here you are applying VDS voltage, and here you are, let's assume this is a black box. So you have two nodes. At this port you can apply VGS, at this port you can have VDS, and from the VDS you can have your output current ID. If you are not able to understand, this is my MOS, right? MOS is there in a black box. It is kept closed in a black box. This is my gate. This will be my source, right? This will be my source only. This will be my drain, and this will be my also my source. Gate source, drain source. This is my black box, right? VGS, VDS, and there is this black box. So if I apply VDS, I will get some current ID. This is what I am talking about in saturation region. So I keep the value of VGS and VDS and VT such that my MOSFET is working in saturation region. Now I am taking the ideal case. In ideal case, what do I observe? If I keep on increasing VDS value, there is no change in ID. What is the formula of resistance? R ohm that I am talking about. I shouldn't write R ohm, it should be RDS only. Drain to source ohm resistance in saturation. So what will be that RDS value? That RDS value will be del VDS. Okay, this is written wrong actually. Del ID upon del VDS. No. This will be 1 upon RDS. 1 upon RDS. So what will be my RDS? The change in VDS voltage and the change in ID voltage. Even if I change this, the current is constant. So del ID is 0. Whatever the change I make in del VDS, let's assume I make the change in del VDS, that is X. But the change in current ID is 0. That means the resistance would be infinity. Are you getting this point? So in case of saturation region, the drain to source own resistance, or you can say output resistance. So in case of saturation region, for ideal case, output resistance is infinity. So del ID by del VDS is 0, or you can say that here the slope is 0. That means del ID by del VDS will be 0. The slope is 0. That shows that the resistance is infinity. But that is the case when there is no channel length modulation. That means when the case is ideal. For ideal case. But let's check for practical case. So practically what is happening? So this was our source, and then this is our channel. This is happening at VDS equals to VD set. Now if you further increase VDS, what happens? Your effective channel is getting reduced. Initially the channel length was L. You can say that in my complete channel there are some charge carriers. Now your effective channel is reduced. Here I showed you your effective channel will keep on reducing. So now your effective channel is reduced. Let's assume it is reduced by delta L. It is reduced by delta L. Your effective channel is reduced by delta L. Right? Now what will be your current equation? The current equation will be mu n cox w by 2L. But instead of L, I will write L minus delta L. Why will I write L minus delta L? Because your effective length is reduced. That's why I will write L minus delta L. And then the same VGS minus VT whole square. So I will write down this equation again here because we are doing the derivation. So what is the current? That is mu n cox w by 2. The length is reduced, L minus delta L, and VGS minus VT square, that is same. If I keep this L out, what will happen? Mu n cox w by 2L 1 minus delta L by L into VGS minus VT whole square. Mu n cox w by 2L VGS minus VT whole square. What do I do with this? 1 minus delta L by L. I can write it like this: 1 minus delta L by L inverse power. Are you agreeing with this point? 1 minus delta L by L inverse power. Well and good. I can write it in this manner. Now what is this? This is ID sat in ideal case. ID sat in ideal case. Mu n cox w by 2L VGS minus VT whole square. So this is ID sat in ideal case. ID sat ideal. ID sat ideal. Now look, this channel length is reduced, but this delta L is very less. I am saying that the channel length is reduced, but delta is not that much large. This delta is very less. So this complete portion will also be very less. This complete portion will also be very less. So one approximation, you know, that 1 minus x to the power minus 1 can be approximated to 1 plus x, right? If x is very low, it can be approximated to 1 plus x. So similarly, you can do, that is delta L by L. So this is, I am getting ID set. ID set when there is channel length modulation. Channel length modulation. Why it is called channel length modulation? Because here the channel length is getting changed. That is channel length modulation. Now there is one thing. This delta L by L is proportional to VDS. Are you agreeing with this point? As much more positive voltage you apply, if you increase VDS, what will happen? Your channel will be more depleted. If you increase VDS, your channel will be more depleted. Your delta L will increase. If you increase VDS, your channel will be more depleted. That means your delta L will increase. So delta L by L is proportional to VDS. If you remove the proportionality constant, you get delta L by L is equals to lambda VDS. Delta L by L is equals to lambda VDS. This is equation 1. This is equation 2. So here delta L by L you can put here. I am adding a page. So what will be your ID set when there is channel length modulation? That will be equals to ID set for ideal case ID set for ideal case and 1 plus delta L by L will be replaced with lambda VDS. Lambda VDS. This will be the formula. So ideal current only, but here it is linearly depending on VDS. 1 plus lambda VDS. What is lambda? Lambda is known as process technology parameter. Lambda is some process technology parameter. Technology parameter. What will be the unit of lambda? What is the unit of 1? Unitless. So if this is unitless, something in addition will also be unitless. So this also has to be unitless. So what should be the unit of lambda? Voltage inverse. Because voltage inverse into voltage, that will make it unitless. So lambda should be voltage inverse. So unit of lambda is voltage inverse. So this is what this is what you understand, that this is the expression. So this is only you need to remember. Even if you don't remember the derivation, it is fine. But derivation is very simple. Effective length is reduced, so L you can take outside, then 1 plus delta L is there. Delta L by L is proportional to lambda VDS. So 1 plus lambda VDS, you can simply put lambda is the process technology parameter. Understood? Now there is a term called, okay, we will go to early voltage later on, but first let's check this drain to source on resistance for saturation region. Drain to source on resistance for saturation region. One more condition is there, channel length modulation is present. Now the channel length modulation is present. What is the formula of RDS? RDS is 1 by del ID upon del VDS, right? Or you can write del VDS upon del ID, or I can write 1 by del ID upon del VDS. You have to differentiate it with respect to VDS. What do you get? You have to differentiate it with respect to VDS. What you will get? This is a constant quantity. So that will come as it is, ID set ideal. If you differentiate this, what you will get? 1 is constant, it will be 0. 0 plus lambda is constant, it will come outside. VDS, differentiation of VDS with respect to VDS, 1. So here you will get 1. So if you del ID upon del VDS is lambda ID set. So what you will get? 1 upon lambda ID set here. Simple differentiation is there. ID set will come outside, and differentiation of VDS with respect to ID. Sorry, del ID upon del VDS. Differentiation of ID with respect to VDS will give you lambda here. That will be 1 upon lambda ID set. This is for ideal case. So if they are asking you RDS value, if they are asking you the output resistance in saturation region, if they are asking you the output resistance of MOS, what you will do? 1 upon lambda IDS. That's it. And if lambda is 0, that means no channel length modulation. Lambda 0 shows no channel length modulation. Then your R0 will be infinity. So basically this is the ideal case only. This I am talking about ideal case. So in ideal case, lambda will be 0. This was ideal case. This complete was ideal case. So in ideal case, your lambda will be 0. There will be no channel length modulation, and your R0 will be infinity. Well and good. Let's move on to one more concept, that is early voltage. What is early voltage? What is your ID? ID set when there is CLM present. That is equals to ID set ideal into 1 plus lambda VDS. This is your ID set, right, in channel length modulation. When will this current be 0? To put this current equals to 0, put this current equals to 0. ID set in channel length modulation. To put this current equals to 0, what should happen? 1 plus lambda VDS should be 0. VDS will be minus 1 by lambda. So the value of VDS, at which the drain current becomes 0, that is known as early voltage. Early voltage. So your early voltage is 1 by lambda. And in the graph I showed you, what did I show you in the graph? If you increase it in previous, this early voltage will be. Conceptually it will never be used. Conceptually early voltage will never be used. But sometimes in the question what they can do, they can give you the value of VA. That they will say that your early voltage is some 200 volts. Early voltage is some 200 volt. Then what you will think, okay, my lambda will be 1 by 200. So lambda is there. From there I can find the value of R naught. That will be 1 by lambda ID set. So 1 by lambda is basically 200 by ID set. ID set in ideal case. In ideal case I can find ID set. Let's assume that is 0.02. So your R will be some 10 to the power 4. R naught will be some 10 to the power 4. So in the question it will be sometimes used. So they can give you the early voltage. That early voltage is some 200 volt. So from there you can find the value of lambda, and from there you can find the value of R naught. So in questions it can be used. So that's why I told you here. So what is early voltage? The negative value of VDS at which the drain current becomes 0 when channel length modulation is present. Well and good, that is early voltage. Now one last concept is left, that is body effect. So when we were studying MOSFET, what did I tell you? What did I tell you? I told you that source I am taking as reference, and I told you that I am shorting source and body. I told you that my source and body are always shorted. This is what I told you when we were studying MOS physics. Now, what if my source and body are not shorted? I am taking again source as reference. Now, what if I put body to be negative? What if I put body to be positive? And what if both are shorted? What will happen in the circuit? Sorry, not in the circuit. What will happen in the device? So that we will see. But before that, I will take a break of 1 minute. Then we will start. So if I put some bias on body, whether it is positive or negative, it will change my VT voltage. It will change my threshold voltage. So let's check that. If my VSB is 0, what happens? There is no change in threshold voltage. No change in threshold voltage. In threshold voltage. Now what do I mean by that? Let's assume I go to a market and I say that, sir, I need an NMOS. So he will give me an NMOS. Okay, so I am having an NMOS. Now he will say that the NMOS that you are having, that has the threshold voltage of 0.7 volt. I went to market, I asked for an NMOS, he gave me an NMOS. He is saying that the NMOS that you are having, that has the threshold voltage of 0.7 volt. What does he mean by that? He means that if your source and body are shorted, if there is no potential between source and body, then your threshold voltage is 0.7 volt. This is what he means. If he is saying the threshold voltage is 0.7 volt, if I am saying the threshold voltage of my NMOS is 0.7 volt, that means my source and body are shorted, then this threshold voltage is there. If I apply some negative bias or positive bias on body, the threshold voltage will change. So that is the scene. So there is a formula which you don't need to remember, but I am just writing it. Vt equals to Vt naught plus gamma 2 phi f plus Vsb minus root 2 phi f. threshold voltage of NMOS. Of NMOS. What is this VT naught? That VT naught is that 0.7. If I am saying my VSB is 0, if I put VSB here equals to 0, so I will get VT equals to VT naught. What is this phi f? That is work function. Sorry, not work function. This is surface potential. Phi f is surface potential. Phi f is surface potential. So you don't need to think about it much. Let's move on to our concept. We will come back to that formula later on, but let's move on to our concept. Now I am saying my VSB is positive. What do I mean VSB positive? That means my base potential is negative, because again I am taking source as a reference. So my base potential is negative. According to that formula, what should happen? The threshold voltage should increase, and it will increase. Why so? That I will tell you. This is source which is at 0. Body is at negative now. There is a diode. This is P substrate and this is N. So diode is something like that. Here you are having negative potential, and here you are having 0. Negative and 0. What you are doing, if you are applying negative potential at base, what you are doing? You are increasing the forward bias. Increasing the forward bias. Right? Okay, I'm sorry for that. Just brainwashed. Increasing the reverse bias. What you are doing? Increasing the reverse bias. If you increase the reverse bias, at the source side, if you are increasing the reverse bias, what is happening? The depletion width here will increase. If the depletion width is increasing, that means there will be strong electric field in this direction. Now there are electrons. What does the source do? What is the work of source? To provide the electrons to the channel, and it will get out of the drain. The work of source is to provide the electrons to the channel, and it will get out of the drain. Now you are increasing the reverse bias. Because of that, the depletion width is getting increased, and because of that, there is high electric field. Now this electron will try to move here in the channel, but there is this high electric field that will give the force to electron in the opposite direction. Applied negative reverse bias, depletion width increased, electric field increased in this direction. Now there are electrons who wants to move in this direction, but since there is very strong electric field, the electrons are not going here, the electrons are pushed back into the source only, in this N plus only. In N plus only, the electrons are pushed back. So electrons are not even reaching towards the drain. So less electrons are reaching towards the drain. So to get more electrons now, what do you need to do? You have to increase the VG potential. That means you have to increase the threshold voltage. Previously, when Vg was equals to Vt only, you were getting some current. But now the electrons are not even reaching there. So you have to increase the Vg potential so that the electron supply can be done from the battery, and electrons reach here, and there will be electrons in the channel. Now what is happening? Since the reverse bias is so strong and the electric field is so strong, the electrons are not even reaching there. So for that, you have to apply a higher VGS value. That means you have your VT will increase. So if base is at negative, sorry, not base, if body is at negative potential, that means your VT will increase. Now one doubt people can get. What is that doubt? That doubt is, sir, you are saying that here the reverse bias is getting increased. This is what you are saying. But sir, one thing is also happening, that I can make a diode here as well, and this side you are applying negative potential here, and at the drain we already apply positive potential. That means the reverse bias is getting decreased at drain side as well. So if reverse bias is getting decreased at drain side, that means there will be higher electric field that will attract the electrons, because the electric field will be in this direction. The electric field will be in this direction. This I have already explained in MOS physics. So this electric field will be in this direction. So the reverse bias at drain side is also getting increased. So high electric field, that means that will attract the electrons very fastly, and the current should increase. That means the Vt value should decrease. This is what you can think. But here, the electrons are not even getting out. The electrons are not even getting out of source terminal. Then what is the point of this high electric field towards the drain? I admit there will be high electric field towards drain, but electrons are not even getting out. So what is the point of that high electric field? So first the electrons has to get out of the source. Then this electric field will be useful. If the electrons are not even getting out, what is the use of this electric field? No use of this electric field, right? So here, what is more dominating? The dominating part is this electric field. This is the dominating part because this is not even letting the electrons get out of the source terminal. I gave you the example of that tap. Your hole of water, that tap was there, no? That tap. Let's assume this hole is very large. मान लो ये बहुत बड़ा होल है यहाँ से पानी आने का. That hole is very large. But if there is no supply, what is the use of this hole? What is the use of this hole? जब पानी आ ही नहीं रहा है तो कितना ही बड़ा होल कर लो, कितना ज्यादा पानी आ जाएगा, नहीं आएगा. But we need water. We need the supply of electron. The supply of electron is reduced. So for that we have to apply higher Vg potential, and then that will increase the Vt value. Understood this concept? Even if you are having doubt, that is also clear. So this doubt is clear. And also in the formula you can see if VSB is increased, then this factor will be increased. High factor minus low factor, that means the overall factor is positive, so the Vt value will increase. So in the interviewer, this is the favorite question of interviewers, that I can keep it like this. I can make a few more things here. So when there was VSB was 0, let's assume this much was the depletion region. This much was the depletion region when VSB was 0. Why this much was the depletion region? Sir, there is no supply. Why there is depletion region? In PN junction, even if there is no supply, there is depletion region, right? Even if there is no supply, the depletion region is always present. If there is positive supply, the depletion region will be reduced. If there is negative supply, the depletion region will increase. So even if there is no VSB, still there is this depletion region. Now if you are applying VSB to be positive or VB to be negative, then this depletion region is getting increased, right? Because you are increasing the reverse bias here. Also the reverse bias is getting increased here as well, but that is not dominating. Dominating is this part because you are not even getting the supply of electron. So this depletion region is increased. Depletion region is increased. So this is the case for VB negative, or you can say VSB equals to positive. VB negative or VSB equals to positive. And this was the case for VSB equals to 0. So let's write it down. So when VB equals to negative, what you are doing? Reverse bias at source side is getting increased. Reverse bias at source side is getting increased. What will happen? Electrons from source will feel high electric field pushing them back into the source terminal. Pushing them back into the source terminal, and for that you need a higher Vg. Yeah, so electrons will feel a high electric field, so that will push them back into the source terminal, so you need high Vg. Higher Vg required, and because of that, what will happen? Vt is increased. Vt is increased. Well and good. Okay. Now we will check for VSB equals to negative. Third case is when VSB is equals to negative. VSB is negative, that means your VB is positive now. VB is positive. So now if VB is positive, as per the formula, what should happen? Here VB is positive. If VB is positive, what should happen? VB is positive, that means VSB is negative. So this factor will be less. So less minus high, that means this factor will be negative. So VT should decrease. And this is what happens. The threshold voltage decreases. So if VB is positive or VSB is negative, the threshold voltage will decrease. Why so? Because here you are having source, this is N and this is P plus, this is negative and this is 0. So 0 and negative. Sorry, VB is now positive. VB is positive. Sorry, VB is positive. So 0 and positive. So what you are doing? You are increasing the forward bias now. You are increasing the forward bias. So this depletion width will be very small. And since this depletion width is very small, the electron can get out of this very quickly. So you need to apply lesser VG voltage. Very easy, just the opposite of this. Depletion width is very small, so electron can get out of this depletion width very easily. So the current will increase. That means at lower VG value only you will get more current. So this source can supply more electrons now. You don't need gate potential for the supply of electrons. You have the source to supply the electrons. So this source can supply more electrons now. Right? Now the source can supply more electrons. Yeah, so this is what I have wrote. Forward bias towards source side is increasing. Source can supply more electrons at lower VG and then VT will reduce. Now people will have one more doubt. They will say that, sir, here also you are decreasing the reverse bias. If you are decreasing the reverse bias, there will be less electric field, there will be less depletion region. That means there will be less electric field and electron will feel less force. So if electron feels less force, then there will be less current. This doubt you can have. But again, there is this explanation that this side is dominating. The source to body size is dominating now. Why it is so? Because even if there is less electric field, but still there are so much of electron. There's so much of electrons are being supplied that even this less electric field can pull these electrons and there will be current. Or you can understand this with the analogy of tap as well. That in the tap, this hole is small, but so much of water is coming. So much of water is coming. So much of water is coming. So there will be large water only. There will be large current only. So at low VGS only, at low VG potential only, you will have large current. The hole is small, but still there are a lot of water is coming. So there will be large water flow. So that means there will be more current. So at lower VG only, you will get more current. So VT is decreased here, and when VB was negative, the VT got increased. So this was the concept, and we can draw it here. This VB is positive. So here the depletion width is getting reduced, but there will so if it is reduced, so there is large flow of electrons and that will increase the current. So at lower VG only you will get some current. So your threshold voltage is decreased. Now the question comes, sir, here the threshold voltage is less. So why don't we always keep base at positive potential? Why do you keep source at 0 and body at 0? We should keep VSB as negative. We should keep VSB negative so that we have the lower threshold and at lower value of threshold we get some current. Now for that my question will be, what was your target for MOS? You wanted to use it as an amplifier, or also you can use it as a switch, but was the target to have lower VT? No. If your VT is in middle, it's fine. Let's draw a graph first. Root ID versus VT. So that will help me to explain my point. Root ID versus VGS. This graph I am drawing. There is this VT1, VT2 and VT3. Let's call this one as VT1, this one as VT naught, and this one as VT2. If I am saying this is VSB equals to 0, so what this will be? VSB equals to positive or negative? Positive. That means your VB is negative. And what this will be? VSB equals to negative. That means your VB is positive. Because at positive VB voltage, if VB is positive, your threshold voltage is less. This value is less than this, than this. So at lower threshold voltage, you are getting some current. But was that your target? This was your target? No. If you keep VB to be positive, what will happen? If you keep VB to be positive, if I am having positive potential here, what will happen? This is N, this is P, and here positive potential is there. Now this diode will drive some current, and that is unwanted. There will be unwanted power consumption in body diode. In the MOSFET, there will be unwanted power consumption. If my VSB is 0, if my VSB is 0 volt, this will be also at 0 volt. This will also be 0 volt. There will be no current in the diode. The diode will not drive any current. If both source and body are shorted, there will be no current in the diode, so that diode will not drive any current. If diode is not driving any current, so there is no power consumption. So if you are keeping VSB positive, sorry, if you are keeping VSB negative, that means if you are keeping VB to be positive, you are having unwanted power consumption. What was the issue when VSB was negative? What was the issue when VSB was positive? That means if VB was negative, so the issue was that our VT was getting increased. So this is also not we want, that I don't want VT to be increased. And if VSB is positive, what is the issue? There is unwanted power consumption in the body diode. There is unwanted power consumption in the MOS circuit, and this is not I want. So that's why I keep VSB to be 0 only. So there is always some issue with VSB positive as well, with VSB negative as well. So when first thing is, when VSB was positive, or you can say VB is negative. This seems more intuitive. VB is negative. Okay, so if VB is negative, that means VT will be increased. VT will be increased. This is not desirable. Not desirable. And secondly, if VSB is negative, or VB is positive, then what will happen? This is N plus, and then this is P substrate body, P body I am writing, and this is at positive. So it will drive some current, and because of this current, there will be unwanted power consumption. Unwanted power consumption. And this is also not desirable. That's why we always try to keep VSB equals to 0 volt, or I can say source body shorted. source body shorted, or at least the minimum forward bias, at least the minimum forward bias, or I will write at least minimum forward bias. Understood this point, minimum forward bias? What do I mean by minimum forward bias? That means here I will have minimum forward bias. If there is something in my circuitry that I cannot keep source and body shorted, so I will ensure that my body potential is such that I am having minimum forward bias, at least minimum forward bias, so that there is no unwanted power consumption. Well and good. Okay. Yeah, one correction I would like to make here is that this correction is that I shouldn't write at least minimum forward bias. My target would be to get the optimum threshold voltage. If I am not getting that, that means if I am not able to keep my source body shorted, if I can't keep this thing VSB equals to 0, then I will try to keep VSB in negative bias only. I will try to keep that in reverse bias. VSB equals to positive. If VSB is positive, that means this is positive, this is 0, source is 0 and body is negative. So I will try to keep the diode in reverse bias so that there is minimum leakage current. There is no current in the diode. Even if my VT is increased, that is fine for me. VT is getting increased, that is fine for me. What will be my first target in the IC? If I am designing an IC, what will be my first target? My first target will be source and body should be shorted. If I am not able to achieve that, what I will think second? My second concern will be the power consumption. I don't want high power consumption. VT is increased, that is understandable, but I don't want high power consumption. If I keep VSB negative, that means if I keep VB to be positive, I am increasing my forward bias between source and body. And if I increase my forward bias, there will be current increasing that, and that will lead to unwanted power consumption. But I don't want that. So I would keep base at the most negative potential in the IC. Whatever the most negative potential is there, I will keep it there, so that even at least the source and body are reverse biased. Getting this point? If the source and body are reverse biased, I will get higher VT, I will get lesser current, but at least I will not have unwanted power consumption. So I will not say that I am keeping it at minimum forward bias. I will say that I will try to keep it at maximum possible reverse bias. Not maximum possible, I will try to keep it at reverse bias. What will be my first target? My first target would be VSB shorted. If I am not able to achieve that, I will keep VB to be negative or VSB to be positive, because I want my source to body diode to be reverse bias. So, or source and body shorted, or at least source to body diode should be reverse bias. Source to body diode should be reverse biased. And this all we studied for NMOS, not for PMOS. For PMOS it will be opposite. First thing is that you would always want source and body shorted, but in case of PMOS, what will happen? Here it will be P positive, so your diode will be something like this. So you would want to keep VB to be positive, so that it is more reverse biased, and if it is more reverse biased, there will be less power consumption. So in case of PMOS, if VB is positive, then VT will get higher, and if VB is negative, then VT will get lower, right? And best thing you would want is source and body are shorted. If they are not shorted, you will try to keep VB to be positive, so that there is no unwanted power consumption in the diode or in the MOSFET. Are you getting this point or not? I hope you have understood the complete MOS physics. I hope you have understood the complete whatever the phenomena, whatever the concept that I wanted to deliver. Now understanding MOSFET amplifiers, MOSFET biasing, it will be very, very easy for you. That's why I took so much time in MOS physics. People will say that this is needless, this is not relevant to gate examination, this is not relevant to analog electronics, this is not relevant to placements, but everything is relevant. Once we will deal the question, you will realize everything is relevant. So after this, we will try to solve the assignment, and I hope you have understood all the concept. Okay, so if you found the video helpful, you can share it. Thank you.